Hello, everyone. Today we are in the second live broadcast for. Hello, everyone. My name is Dipankar Pal, and today we are doing the second broadcast for lectures on crystal plasticity. So, as we discussed last time, we will be doing basically we'll be working our way out with respect to Miller indices. And basically, with respect to Miller indices, we'll be talking about uh, how to actually identify Miller indices. And, by definition, Miller indices are a way of identifying crystalline planes and crystalline directions. And with respect to what we have discussed last time, crystalline materials are nothing but periodic array of atoms, molecules, or other types of atomic motifs which are put together in a periodic array of in a periodic array, if you will. So what we are going to do now is basically we'll try to understand how this aspect of periodicity works, and how in a very standardized format we try and understand what are a set system of crystalline planes, set system of crystalline directions, if you will. So here goes Miller indices. So in order to understand Miller indices, first you have to have some good knowledge about um, coordinate geometry. So for example, most of the crystalline systems which we will be discussing today are cubic crystalline material types. So for example, all of these materials will have their coordinate system at origin 0, 0, 0. Let me make sure why it's not okay. So yeah, so they have a crystalline coordinate system 0, 0, 0, and then basically as you go, so this is your x direction. It will have the coordinate of 1, 0, 0 over here. Then we'll have a coordinate. Now this is your y direction. We'll have a coordinate of 0, comma 1, comma 0, and then this one over here of 0, comma 1, comma 1, if you will. Now, as soon as we start going in the z direction, which is the z axis over here, everything gets appended by unit 1 in their z direction. Sorry, this should be, this here should be 1, comma 1, comma 0. And then everything gets appended by 1 in the third direction. So this will become 1, comma 0, comma 1. This coordinate system will become this coordinate over here. This will become 0, comma 0, comma 1. This will become 0, comma 1, comma 1. And this last one will become 1, comma 1, comma 1. So that's how you will start looking at the entire cubic crystalline lattice or cubic crystalline periodic unit at the atomic or at its most fundamental length scale. It could be a motif of atoms, it could be a motif of molecules. However, it is, you'll have these eight coordinates which are of interest to metallurgists. And then basically how we kind of understand the Miller indices. We understand them in terms of directions and planes. So let's say we are talking about the planes. So in terms of planes, for example, let's say we have a plane. This is the z direction. Sorry, this this is the y direction and this is the x direction. And let's say we have a plane which is cutting at 100, 001, and 010. Then what would happen is we know the intercept of these planes. The intercept of these planes are one in the z direction, one in the x direction, and one in the y direction. So basically, when we know the intercepts of the plane, we'll represent it as 1, comma 1, comma 1. And then we'll use close brackets for planes. And then the information which is inside, these are basically your intercepts with respect to x, y, and z axis. Also, if you look at this very, very closely, what is happening is the direction of the normal, which is passing through the plane. If you do the projection of this normal, so what we'll do in terms of the projection is basically we'll take this length, and then basically we'll start to you know creates a shadow in the x, y, and z directions. And we'll see that the intercept information also coincides with the direction information, as in you have to move one unit in the direction of x, followed by one unit in the direction of z, followed by one unit in the direction of y, followed by one unit in the direction of z, to have the same normal. So that's why the information which you see inside these Miller indices are indicative of not only the intercepts but also how much information is incorporated in there with respect to the normal directions of the plane which we have over here. So either you can think about this information in terms of the normals, or you can think about this information in terms of various intercepts, if you will. And for planes, you just use close brackets. If you have to show a family of planes, then you use these curly brackets for family of planes. And what do we mean by family of planes? So let's say we put 1 comma 1 comma 1 inside this. How this curly bracket is different from this close brackets with respect to the Miller indices of these particular planes? Let's try and understand more. So in terms of the curly brackets, what starts to happen is that you are not only talking about this plane anymore. So this was the initial plane which we just talked about, and it had the intercept 1, 1, 1 in x, y, and z direction. So we are not only talking about this, but we are also talking about this other plane, this plane, and the other plane over here. So whenever the intercept magnitude is 1, irrespective of its positive or negative, then basically we are talking about the entire family of planes. So this can have plus minus 1, two combinations. This could have plus minus 1, two combinations, and this could have plus minus 1, two more combinations. So 8 combinations are possible with respect to a family of a certain plane when it comes to cubic crystalline materials. So you can think about having minus 1, 1, and 1 also as a plane where the intercept in the x direction will be minus 1. So if you think about this x, y, and z, this will be minus 1. but then this is positive 1, and then this is negative, then this is positive 1 in the z direction. So this combination -1 1 1, instead of writing another pair of crystalline plane for this particular planar system, what you can do is you can incorporate this information over here in terms of these curly brackets. And when you write these curly brackets and you incorporate the information 1 1 1, this is basically the mod value of that mod or absolute value of the intercept you are talking about. It can either have the minus information or you can have the plus information in there, right? So -1 comma 1 comma 1 is already contained in this in these eight in these eight types of in these eight crystalline planes which we are talking about here in terms of these curly brackets, if you will. So and that's how we understand when we are talking about a crystalline plane, and then a family of planes. In coordinate geometry, if you have done some of these 3D geometry incorporations, if you have studied 3D coordinate geometry before, there are always a single plane. We either talk about a single plane, which we are interested in, or we talk about a family of planes which share certain characteristics. And similarly, in crystalline geometries as well, you can have a single crystalline plane, for example, this 1 1 1 over here, or you can have this 1 1 1 in curly brackets, and then you suddenly start talking about all of these planes which have this shared attribute of having one as its intercept in x, y, and z direction, but then whether it's -1 or +1 with respect to crystalline axis, that can be further seen in terms of this entire family, and you always have these eight things, or eight crystalline planes which you are essentially talking about when you are talking about this curly brackets, if you will. So yeah, this is basically a standard practice in crystalline materials, how you represent a plane. And these particular planes, as we go along in this lecture or in this talk today, we'll discuss more about how these planes suddenly become very very important in order to understand how the slip kind of takes place. So yeah, so this is the basic understanding of crystalline planes. Now we'll go try and understand what are crystalline directions. So crystalline directions comes from the shadow methodology or the projection methodology which we talked about earlier, in terms of the normal of the plane. uh, so for example, if we have in this plane, so this is your x-axis, your y-axis, and z-axis. And let's say in the xz plane, we have an arrow direction like this. Then basically we have to first go 1 unit in the direction of x, and then 1 unit in the direction of z. So this direction vector can be given by a square bracket 1 comma 0 comma 1, and this is basically the direction vector. So this has much more similarity with respect to three-dimensional coordinate geometry, or in terms of vectors, how we understand vectors. You have how much you have to traverse in the x direction, y direction, and z direction, and then basically you create a unit normal vector in that particular direction. So for example, with respect to this direction over here, you will multiply by a factor of 1 by square root 2 in order to make it unit you know a unit vector in that particular direction, if you will. And 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 in order to understand the family of these, you represent them using an angled bracket. So for example, when you are writing 101 using an angle bracket, what does it mean is that you're not only talking about this particular direction, but you're talking about all possible directions, positive or negative. Again, eight directions you're talking about. But for this particular thing, you might have only four directions because you have a zero over here. So you can have positive, negative one, positive, negative one. So there are only four combinations possible. So you will write this as 1 by root 2, 101. So this is a possible direction, this is a possible direction, and this is a possible direction. Sorry, excuse me. This is another possible direction. So until and unless you are inside this, so this is positive x, this is negative x, this is negative z. So these four directions are all possibilities when it comes to writing this direction in terms of the angle bracket, if you will. So this pretty much sums up what we need to understand in terms of crystalline planes and crystalline directions. So basically, crystalline planes can be understood either in terms of their intercepts, or they can be understood in terms of their normal vectors. And what we need to understand further is that whenever there is a minus one associated with either a direction or a vector, so for example, if we talk about this particular direction, then this has to be represented as 1 by root 2. First, you will go 1 in the positive x direction, 0 in the positive y direction, and then negative 1 in the negative 1 in the minus z direction. So for this particular case, if you will, you don't write things as negative anymore. What you do is you write things as 1 by root 2, 1, comma 0, comma 1 bar. So whenever you write bar 1, that means that you are indicating the negative aspect of that particular number. And that is true also about the planes. So remember when we were on the previous page, if you will, when we talked about this negative 1 comma 1 comma 1, we have to write this in terms of the standard notation as 1 bar comma 1 comma 1. And when we are putting this particular um, closed bracket, that means we are just talking about this particular plane. But when we are talking about that curly bracket, then it means that it could be one of those eight planes. And depending on how many ones and zeros are present, you can have either eight combinations possible, four combinations, or two combinations possible with respect to planes, and that's same for your directions as well. You can either have two combinations of directions or one combination of direction, two combinations, four combinations, or eight combinations of directions as a possibility with respect to crystalline directions, if you will. Now, why do we need to understand these directions and these planes, if you will? We do need to understand them because they are fundamental in understanding how slip occurs in certain directions and certain planes. All right. So let's talk about there is one type of crystalline system which is very famous, and that is called a face-centered cubic system. So, for example, when we are talking about nickel, material nickel, and copper, and all those types of highly ductile materials, they generally have this face-centered cubic material structure, crystalline material structure. And what do we mean by that? What do we mean by that is that if you draw this cubic lattice at the atomic level, and basically this is the fundamental unit, and then there is periodicity in x, y, and z directions. What is happening, and we'll also talk about its defects. So this is just a way of making it understand in terms of how how we understand face-centered cubic materials. We're not talking about defects anymore over here. but we'll be talking about the defects and how things change. But from a fundamental understanding, what really happens is, when we talk about face-centered cubic, basically you have an atom at this face-centered, you have atoms at the corners, and basically each plane has similar attributes, where you have atoms at the center of the plane and atoms at the corners. But if you look closely enough, what happens is, if you take this particular plane, what happens is, if we are looking at that plane, that particular plane, what happens is there is an atom over here and atoms there as well. But in terms of most of the materials which have this face-centered cubic type of crystal structure, these atoms actually start to touch on the phase diagonal. So this is one of those. So let me correct this particular drawing over here. And we'll have certain discussions with respect to microstructure of polymeric materials, amorphous polymeric materials later. But with respect to crystalline materials, what happens is these atoms touch at the face, along the phase diagonal. So basically, what happens is, in terms of the atomic radius r, if let's say all the atoms have this same atomic radius r, you have r coming from 1/4 of that particular atom in the plane. With respect to the 3D, it's actually 1/8, but with respect to this 2D projection of that particular plane, uh, no. So basically, this is the entire 3D, but we are just looking at this 2D image from this side. So you have R, 2R, and R. So this is 4R, and this is called crystal lattice spacing. So A is your crystal lattice spacing. So your 4R becomes A times root 2. Why this is A times root 2? Because if you do Pythagoras, this is A and this other length is also A. So if you do Pythagoras on top of it, this is A square root 2. Also, this is a square. If you put a 45-degree angle using your trigonometric identities, you'll get A square root 2 over here. So if we divide both sides by 4, then we get A square root 2 over 4, and your atomic radius is A by 2 root 2. So if you know the crystal lattice spacing, and crystal lattice spacing is something which we can identify using different types of experiments such as X-rays and others, then if you divide by 2 root 2, then you basically get the atomic size spacing, the atomic radius from this particular calculation. All right. The other way of looking at it is to understand how much is the population density of these spheres inside this particular cube. Okay, so let's see in terms of this particular cube how many spheres are present to begin with. So if you look at this particular cube again, there is 1/8 contribution which is coming from this corner atoms. So basically, you have 1/8 contribution from 8 corner atoms, plus these face-centered cubic atoms each give around half contribution, because each plane, each of these side planes are shared in between two cubes. So basically, you will get half contribution from, and then basically, if you look at the number of sides which are possibilities on this particular cube, then there are six possibilities, right? The top and bottom plane, uh, left hand side and right hand side plane, towards you and away from you plane. So um, there are six face centered atoms, half contribution from six face centered cubic atoms. So from face centered atoms, right? So basically, if you look at this particular combination, then the total number of atoms in FCC, or face centered cubic, is 1/8 times 8 of corners plus half times 6 of face centers. So basically, you are getting one atom from the corner contribution and three atoms from the faces. So basically, you're talking about total of four atoms over here. We know the atomic radius herein. We know the volume of the cube. So volume of the cube is nothing but a cubed of this entire cubic structure. Then and we know that there are four atoms which are inscribed uh, inside this cubic structure. So volume of four atoms incorporated in FCC is nothing but 4 times 4 by 3 pi r cubed. So, so if you would like to write the packing fraction of FCC, that comes out to be 4 times 4 divided by 3 pi r cubed, 4 divided by 3 pi r cubed being the volume of one sphere, times 4 because there are 4 atoms which we are talking about, divided by a cubed. And this could be further written as, so from uh, previous identity over here, this a can be written as a equals 2r root 2. So this can be written as 2r root 2 cubed, 16 by 3 pi r cubed. This could be further written as 8 times 2 root 2 r cubed, 16 by 3 pi r cubed. So r cubed and r cubed will cancel, 16 and 16 will cancel. So what you get at the end of the day is pi divided by 3 in the numerator, divided by root of 2. So this comes out to be pi divided by 3 root 2. This is 3 1.414. This is 3.14. So we are talking about, somewhere around 3.14 divided by 4.2. So this, on doing further calculations, if you will, this calculation will be around 72%. And that's pretty much clear because if you take 3/4 of 4.2, that's around 2.1 plus 1.05. That's around 3.15, and that's, is zero point zero 0.01 bigger than the pi number over here in the numerator, and that number comes to be about 72%. And this trick could be used in numerous applications. So, for example, some of in some fairs they ask, they have a cylinder and they fill that completely with balls and tap it. So then you already know how many how many you can actually do a calculation first correlating the radius of your balls with respect to the cylinder radius, or other dimensions of the cylinder, and then can figure out what is the packing fraction and then back calculate how many balls could be present. So anyway, that is something which people use from time to time to understand, to figure out how many, to win prizes and things like that. But the same analogy can be can be stretched over here. So basically, for cubic crystalline lattices, this is the maximum packing fraction of atoms which is possible volumetrically in these materials. And this 72% is a very good number in terms of how to closely pack atoms, one with respect to another, to fill up space in these face-centered cubic materials, if you will. Now, why what we have understood in terms of crystalline directions and planes become important is because of the fact. So we were just discussing when we were discussing about the face centers, we were saying that this particular direction, if you take one particular phase of of that crystalline FCC material, what we were saying is that these these atoms are closely touching one another in the face and in the phase diagonal direction. And since they're touching in the phase diagonal direction, this is the direction in which the slip happens. And we'll talk more about slip, how macroscopically you incorporate the load, and then how it finds a particular direction in which there is maximum shear, and how that correlates with this particular direction. We'll try to understand the macro micro correlation, and then how the micro contribution goes back to the macro aspect. But from the local crystalline coordinate system, this particular direction becomes very, very important and interesting, because this is the direction um, in which maximum slip can occur. And this is the direction which is the most closely packed. So we talked about volumetric close packing in terms of that 72% number which we just derived, but this direction by itself is also very, very important, because this is the direction of maximum close packing. And this direction becomes the slip direction. So when we see this in terms of the FCC lattice over here, this plane, or some or uh, planes similar to that in the top, bottom, towards you, away from you, left and right, you'll have these planes which are that curly bracket explanation of of those planes. So these planes are the maximum close patch planes called the slip planes. And then if you look at this particular plane, this particular direction, these two directions are slip directions. Okay, so basically this direction over here is nothing but this direction. And if this is x, y, and z axis, we are talking about this direction in terms of 0 comma 1 comma 1 divided by square root 2, if you will. So, and then if you are talking about the entire family of these directions, we'll talk about um, 0 comma 1 comma 1. And since all these family of directions are possible, divided by square root 2, 1 comma 0 comma 1 divided by square root 2, and 1 comma 1 comma 0 divided by square root 2. So these are the most probable direction in which the deformation will occur through slipping. Slipping is nothing but shear motivated or shear dominated way of performing deformation, and we'll talk and learn more about it, that how the macroscopic shear can be incorporated or correlated with this microscopic slip in our further chapters. But for today, what we understood is how we define our crystalline planes and crystalline strip directions, if you will, how we compute the packing fraction in terms of volumetric densities, if you will, and then how certain directions and certain planes for known materials which have, for example, an FCC structure, at least the example which we did today, will be more close packed compared to other directions which are possible. So these are the slip directions, and if you want to understand the slip planes, if you will, uh, those will be your 100 slip planes, 0, comma 1, comma 0, and 0, comma 0, comma 1. So, anywho, all these combinations and permutations will be possible in terms of understanding these slip directions and slip planes. And this will go into further computations with respect to crystal plasticity, and how this understanding which we did today will be correlated in terms of when we are talking in terms of finite element methods. Now, this is only for cubic crystalline system. There is an uh, entire field of study with respect to hexagonal closed pack systems. Then there are other crystalline systems where there are organometallics and jewelry is involved, minerals are involved, where there could be a severe plastic deformation which could occur during earthquakes or other geographical events. So we'll understand everything one by one, and we'll hopefully try and extend what we have understood today even further in our future lectures. So in our future lectures will talk more about these Wheeler indices. We'll talk about other crystalline systems, cubic crystalline systems to start with. For example, body-centered cubic. We understood everything in terms of face-centered cubic today. We'll extend it to body-centered cubic. We'll talk about hexagonal close-packed directions. We'll talk more about other aspects uh, such as how to incorporate macroscopic information into microscopic information and vice versa. And then finally, how everything is incorporated in terms of crystal plasticity, and how that paves way for further understanding of amorphous plasticity, if you will, and how those two could be correlated for a generic mesoscopic modeling of all types of materials, if you will. So we'll take one step at a time, and thank you again for joining me today. My name is Dipankar. I'm from ANSYS, and as always, we hope we hope uh, and we are here to help you further in this journey of taking one step at a time towards ICME from a material system understanding, and then how this knowledge can be incorporated in terms of numerical analysis, and then how we can tie in process property, process microstructure property together in terms of macro aspects, and then different length scales with respect to each of these entities of ICME further. So with that, I hope and believe that you will give answers a chance for solving your simulation problems with respect to ICME, multi-scale, and crystal plasticity arenas. As always, Answers is a world leader in simulation. Thank you for your time today, and have a great time ahead. Have a happy Thanksgiving. Bye now.